right, let's go through the first semester final exam review practice. First one, in your own words, describe the terms mass and volume. So if I get out red here, then I can type in a different color. Mass is the amount of matter in an object or substance, measured in grams. Volume is the amount of space something takes up, measured in milliliters often. Matter is something that has mass and volume. So a lot of times people think that air molecules are not matter just because you can't see them. But air molecules do have mass and they do take up space. Something that's not matter, light and energy, are not matter. What do the symbols S, L, AQ, and G stand for? And then explain the difference between NaClAQ and NaCl. Well, in your final exam learning targets page, there's actually a little table here that I'll paste off to the side. So those are the shorthand symbols for solid, liquid, gas, and aqueous solution. And the difference between NaClAQ is this is salt dissolved in water, and liquid salt, I kind of went on to the next page here, but liquid salt would be salt that's heated to melting point until a liquid. So you have to get it pretty hot because salt has a high melting point. But that would be very different from salt dissolved in water. All right, some measurements here. What are the following measurements? Be sure to include the appropriate number of significant figures. If you haven't already and you've struggled with measurements, I highly recommend checking out this video with some extra practice in the final exam learning targets. So this instrument goes by the ones place because this is 40, this is 45, and then 50. So it goes 41, 42, 43, 44. And it looks like it's somewhere between 43 and 44, and specifically maybe right on the 43. So we don't just write 43. It goes by the ones place. So we always estimate out one more. So if you think it's right on the line, you need to write 43.0. For this next instrument, it goes by the ones place, 6, 7, 8, 9, 10. And so all we can do is say 8.9, and it said that it was in centimeters. A lot of people are tempted to say something like, ooh, 8.97 or something like that, but that would only be if it was measuring to the 10th place, which it's not. It's just going by the ones place. All right, some density questions. So on the final exam, you'll have your reference sheet and reference page, and it has this triangle. So let's just define everything. The M stands for mass, the V stands for volume, and the D stands for density. And you cover up what you want to solve for. So I'm just going to get a random shape here, maybe. Maybe I'm not. Sorry. Okay, I don't know how to do it in OneNote. But let's say you're solving for mass. If you cover it up, you can see what's left is density times volume. So that would be the formula. If you're solving for density, cover it up, and what's left is mass divided by volume. And if you're solving for volume, cover it up, it's mass divided by density. And then the units for each of these, mass is measured in grams, volume in milliliters, which is the same as centimeters cubed, and then density units would be grams per milliliter. Okay, so this says if a piece of zinc displaces 250 milliliters of water, when I see milliliters, I should say, okay, that is a volume. And it's asking for mass, so I cover up mass. So I'm going to need to do density times volume. So I'm going to write out my formula. Mass equals density times volume. And the density for zinc is 7.1 grams per milliliter times the volume, which is 250 milliliters. And I can see that my milliliters are going to cancel out because they're on the top and the bottom. And I'm getting my calculator out because I'm doing these problems for the first time with you. 7.1 times 250 is about 1,800 grams. It's okay if you round differently as long as you show your work. Next question, if a piece of brass has a mass of 125 grams, what volume will it displace? So this time we are looking for volume. So back to this little triangle, I'm going to cross out volume. My formula is mass divided by density. It says it's brass. Our mass is 125 grams. And the density of brass on this table is 8.4 grams per milliliter. So I'm going to type this into my calculator, 125 divided by 8.4, answer 15 milliliters. And the reason I know those units is grams cancels out, and it's 1 over milliliters, so the milliliters flips up to the top. And again, it's okay if you rounded differently, like if you wrote 14.88 or something. That's totally fine. Last one, what is the density of a metal if it's got a mass of 34 grams and it displaces 20 milliliters? And then what is the identity? So this time we want to solve for density, so we're going to cross it out and we'll do mass divided by volume to get the density. That's 34 grams divided by 20 milliliters. I'm typing that into my calculator. Answer 1.7 grams over milliliters. And what's the identity? Looking at the chart, it must be magnesium because that matches the density. Magnesium, no matter what size, always has the particles packed so that 1 milliliter of space equals 1.7 grams. What's the difference between a group and a period on the periodic table? Which are represented by rows and which are represented by columns? So the rows are going across, or in other words, they're horizontal. And those are the periods. And the columns are going vertically. They're also known as groups. Oh, sorry, that is what the answer was looking for. So those are groups. So if we look at the periodic table you'll be given, you can see you're actually going to be given the label period. So like period 3 is all of these that I just drew a line through because they're the horizontal rows. And groups are up and down. Like group 5A, I'm drawing a line through all the elements in group 5A. Identify which family the elements below belong to. So this was back in a coloring the periodic table activity that we did. So you should know the names of basically transition metals is given to you. So 4 groups. Hopefully you're catching on that the last group is called the noble gases. We've talked about them a lot because of noble gas envy and forming ions and the Lewis dot diagrams wanting to have, 8 electrons surrounding them. So the noble gases are referred to a lot. So some of these other groups might be a little trickier to remember, but the halogens are group 7A. And then group 1A is the alkali metals. You can remember that at least, the metals are to the left of the zigzag. Oops, I just noticed I need to put a zigzag on here. And then the group 2A, these are called the alkaline earth metals. So those are the group names. So looking at our question here, it says, what about bromine, number 35? So let's look. Bromine, number 35, is in group 7A. So that means it's one of the halogens. Number 10, neon, that is in group 8A. So that is one of the noble gases. Barium is number 56, right here. So that's one of the alkaline earth metals. Potassium, number 19, is right here. That's one of the alkali metals. And copper, number 29, is right here. That it says right above it is one of the transition metals. Explain the difference between an element and a compound and give an example of each. So an element is one type of atom. So for example, a copper penny, that's pure copper. A compound would be 2 or more elements bonded. So an example would be H2O. That's not on the periodic table. Water is not, because it's a combination of 2 elements. Give 2 examples of each of the following. Provide the name and the symbol for each element. So we've got to give some examples of nonmetals and some examples of metals. Well, just as a little refresher, the nonmetals are to the right of the zigzag on the periodic table, and the metals are to the left of the zigzag. That'd be something, good to have on your notes page, or else you can also remind yourself, because it literally gives you a big hint right here, and it says the transition metals are this middle section. So you can remember, okay, well, that must mean that everything to the left of the periodic table is a metal. So here's one. Sodium, number 11, is an example of a metal. Sodium Na is a metal. And then let's pick another one. Let's pick Sn, tin. It's close to the zigzag, but it's still to the left. So tin, Sn. And then let's pick some nonmetals. I'm actually going to pick one that's not right of the zigzag, just to be difficult and to choose the exception. Hydrogen is the only nonmetal that's to the left of the zigzag. And then let's pick one more nonmetal. How about carbon? It's to the right of the zigzag. So it is a nonmetal. All right, number 11, what is chemical reactivity and where on the periodic table are the most reactive elements and the least reactive? Well, chemical reactivity is the likelihood of something to form a new compound. So, you know, if it's interacting with water or if it's interacting with a metal, for example, and it releases energy, that's a big sign that it is reactive. And you're going to find the most reactive elements on the bottom left. Okay, so if we look here, like cesium and francium, CS and FR. And also the upper right, besides the noble gases. So fluorine, which is a halogen, those are the most reactive. The least reactive are the noble gases. Also, the transition metals aren't very reactive either, but the noble gases, they're already happy because they have the great 8 electrons, so they're not reactive. What's an element that would have a similar reactivity to fluorine? And explain. So, oops, let's go back here. So fluorine is number 9. And you might think, oh, oxygen or neon, because they're right next to it, but it's actually group 7A that it shares characteristics or properties with, because they all have 7 valence electrons since they're in group 7A. So an element that would be similar would be chlorine. So number 17, chlorine. It's in the same group, 7A, as fluorine. And again, you could get deeper and start getting into valence electrons, and they both want to gain one more electron. But I'm just going to leave it as they're in the same group for my explanation at this level. Which 2 subatomic particles contribute most to the mass of an atom? That's the protons and the neutrons. They're both in the nucleus. The electrons hardly weigh anything, so we kind of count them out. We're like, whatever, don't pay attention to them. How about the charge of an atom? Protons have a positive charge, think P and P, okay? And then electrons have a negative charge. Neutrons have no charge. Complete the following table. All of these atoms are neutral. So let's look up calcium, number 20, and find out its average atomic mass. 40.078, which means its most common mass number is 40 because we round to the nearest whole number. Since it's number 20 and it's neutral, that means it has 20 protons and 20 electrons. And to get neutrons, we take the most common mass number and we subtract the number of protons. So in this case, we do 40 minus 20, and it's 20 neutrons. For the next one, we have to look up, okay, which element is number 15, and that's phosphorus, P, number 15. Its average atomic mass is the number at the bottom, 30.974. which would round to 31. So it also has 15 electrons because electrons match the number of protons if it's neutral, which makes sense because positive 15 plus a negative 15 equals 0. And then to get neutrons, we're going to take our mass number minus our number of protons, and that's 16, because the protons and the neutrons contribute to the mass. And then one more here, number 31. Let's look up what element that is. Gallium, Ga. And let's look at the bottom of its periodic table square, 69.723. That rounds to 70. 31 protons, that means 31 electrons. And then we have to do some math here. Let's see, 70 minus 31, is that 39, I think? It's always bad to try and do mental math. Don't follow my lead. Use your calculator just in case. All right, number 15. What is an isotope? It's an atom with the same number of protons, but a different number of neutrons. And therefore, a different mass number. So it says write the isotope symbols for a carbon atom with 6 neutrons and then one with 8 neutrons. So carbon's number 6, and that goes in the bottom left. If one has 6 neutrons, you do 6 plus 6, that's 12 for the mass number. And then 6 plus 8, that's 14 for the mass number. So those would be isotope symbols for those two isotopes of carbon. Now, which isotope is more common? Carbon 12 or carbon 14? Explain how you know. Well, let's look up carbon on the periodic table and notice that its average atomic mass is 12.011. So that means that carbon 12 is the most common. It's closer to carbon's average atomic mass. But of course, there are some carbon 13s and carbon 14s. They're more rare, but that's why the average isn't like a perfect 12. That's why it's 12.011, because those isotopes, although rare, still contribute to increasing the average. All right, now we're in learning target 9. Let's talk about potassium. Potassium's number 19, so that means its atomic number is 19. And let's look at how many shells it has. So potassium is in period number 4. That means it has 4 shells of electrons. Total electrons, assuming that it's neutral, is 19. This is number 19. And valence electrons match the group number. So potassium is in group 1A. So that means that it has 1 valence electron. What element is number 7? Let's look it up. It is number 7 is nitrogen. So let's write nitrogen. Number 7, N. How many shells does it have? Well, let's look what period nitrogen is in. It is in period 2. Since it's number 7 and we're assuming it's neutral, it has 7 total electrons. And then valence electrons always matches the group number. It's in group 5A, so it has 5 valence electrons. Next, we've got to put some atoms in order of increasing atomic radius. Chlorine, sulfur, fluorine, and bromine. So if we look, let's just take a second and clear off some of this craziness here. So we have sort of a clean slate. We are talking, oh no, I erased some of my own charges. Put these back in real quick. Okay, so we're talking about fluorine versus chlorine versus bromine versus sulfur. We need to put these in order of atomic radius. Was it increasing or decreasing? Increasing size. So which one of these is the smallest of all of these options? Okay, so let's look back on here. The smallest will be the one that has the least number of shells. So that would definitely be fluorine. So fluorine is the smallest. Okay, and the reason is it only has 2 shells. But now we're kind of stuck because between sulfur and chlorine, 16 and 17, they're both in period 3. So they both have 3 shells. So the only difference is that chlorine has 1 extra proton in the nucleus. So sulfur has the 3 shells, but the chlorine can pull in those shells a little bit tighter because of that extra positive proton in the nucleus. So that means that chlorine's a little bit smaller than sulfur. Chlorine has 1 more proton than sulfur, pulling in, attracting the electron shells. And then the next one would be sulfur, because it also has 3 shells. But like we established, it's a little bit bigger than chlorine. And last but not least, the largest of these is bromine, because bromine has 4 shells. So shells kind of trumps everything else. Bromine has 4 shells. So it has the largest atomic radius. Which has a larger ionization energy? And I like to just write off to the side like what this is. This means it takes more energy to remove an electron. So would it be harder to take an electron away from sulfur or from chlorine? Remember, chlorine's holding them in a little bit tighter with that 1 extra proton. So chlorine, 1 extra proton in the nucleus pulls the electrons closer. So it's like 2 magnets that are closer together. It's harder to pull them apart, making it harder to remove an electron. Number 20, which weighs more? 6.02 times 10 to the 23rd. Ooh, I recognize that number. That's 1 mole. Which weighs more, 1 mole of carbon atoms or 1 mole of lithium atoms? Be sure to use the term mole in your answer. So according to the periodic table, 1 mole of carbon atoms is equal to the number at the bottom. So in this case for carbon, 12.011 grams. And 1 mole of lithium atoms is equal to 6.94 grams. So which weighs more? 1 mole of carbon atoms, because they're larger than the lithium atoms. If you have the same number of both, the carbon atoms weigh more. They're bigger. And I don't mean bigger like atomic radius. I mean more massive because they have more protons and neutrons. Number 21. What's the mass of 65 moles of sulfur? And that's number 16, S. So this is the dimensional analysis question. So always start with what you know. We've got 65 moles of sulfur. We need to convert this into grams. That's what it's asking for. What is the mass? Well, we need to get moles of sulfur canceled out, and we need to get it into grams of sulfur. So I want to write 1 mole of sulfur on the bottom because I know where I can find a conversion for 1 mole of sulfur. I look at the periodic table. 1 mole of sulfur atoms weighs 32.06 grams. We've got 65 moles of sulfur. Each one weighs 32 grams. So we're going to have a big number here. 65 times 32.06. That's 2,080 approximately. And around to 2,100. It's okay if you round differently. 2,100 grams of sulfur. And I'm going to slash out my moles of sulfur to make sure I did it right. And yes, that's right. Next, 435 grams of sodium. Sodium is number 11, Na. And I want to calculate how many moles that is. So I've got to cancel out grams of Na, and I've got to get it into moles of Na. So 1 mole of Na is equal to how many grams? So let's go look it up. 22.99. 22.99. Okay, this time grams are going to cancel out, and I'm going to multiply everything on the top and divide it by everything on the bottom. So 435 divided by 22.99, that is 18.9 moles of Na. And that makes sense because 1 mole is about 23 grams, and I have a lot more than that if I have 435 grams. So it makes sense that my number will be bigger than 1. All right, now we're in Unit 3. What type of bonding do you expect there to be in the following molecules? All right, on your reference sheet, you get to have this handy-dandy flow chart. So let's review this. If something has all metal atoms, it has metallic bonding. If it has metal and non-metal atoms, it has ionic bonding. And if it has all non-metal atoms, you need to look at further clues. If it's a hard solid, it has network covalent bonding. And if it's a soft solid, a solid that dissolves in water, or it's a liquid or a gas, then it has molecular covalent bonding. So let's look at our first one. It's a gas. So automatically the only one that has a gas as an option is the molecular covalent. NH3, just to double check, those are non-metals. Nitrogen is to the right of the zigzag, and hydrogen is definitely a non-metal. So this would have molecular covalent bonding. Oops, molecular covalent. And the next one, NaCl. Let's find out where they're at. Na is to the left of the zigzag, and Cl is to the right. That means we've got a metal and a non-metal, which means this has ionic bonding. Mg, solid. Mg is to the left of the zigzag, so it's a metal. So if something just has metal atoms, it has metallic bonding. And last but not least, we have H2O liquid. It's all nonmetals and it's a liquid, so it's another molecular covalent. So there wasn't an example of network covalent yet. Letter E says a hard solid, it doesn't dissolve, it doesn't conduct electricity. That is definitely network covalent. That is the boring set of properties. Network covalent bonds are things like SiO2, which is sand. And then a substance that conducts electricity as a solid would be something with metallic bonding. Also, these don't really belong in Learning Target 1. They're Learning Target 2 for Unit 3. I was just noticing that. 24. Will solid copper sulfate, which is a metal and nonmetals, so that's ionic bonding, will it conduct electricity as a solid? No. Salts do not conduct electricity as a solid. But if you dissolve it in water, will it conduct electricity? Yes. Explain. Well, substances with ionic bonding do conduct when dissolved in water because they split up into ions, which allows electricity to flow through. Do conduct electricity in aqueous form. Name a property NH3 gas would form. So this is something with molecular covalent bonding. And one thing that really sets them apart is they have low melting points. That's why it's a gas, because it didn't take much energy for it to turn from a solid to a liquid to a gas. Explain what is meant by noble gas envy. Okay, noble gases have the great 8 valence electrons. They are stable. So all other atoms try to be like them in their electron configuration. So they all try to surround themselves with 8 valence electrons. They can't actually change what type of atom they are, but they can change their electron configuration by forming ions, by gaining or losing electrons. Oops, I need to plug in quick. This is a long review, but this is covering like everything we did the whole year, basically. So keep it up. We got this. Number 27, explain how ionic bonds form. A metal gives its electrons, electron or electrons, to a nonmetal. Oops, a metal or metals to a nonmetal. Yeah, we'll make the option plural. So the metal is now positive, and the nonmetal negative. So they attract, and this is an ionic bond. Okay, and we're going to look at an example of that here in a minute. Would each of the following gain or lose electrons to form a stable ion? And then write the symbol. Okay, let's look at number 19. Number 19, potassium, is right here. And it's so close to being like number 18, right? 19 is closest to number 18 of all the noble gases, okay? It just needs to lose one electron and then it will be like argon. So it will lose one and then the resulting ion will be K+. Now, if you're wondering why, well, if it's neutral, it has 19 protons and 19 electrons, right? And positive 19 and negative 19 add up to 0. But if it loses an electron, now it only has 18. So now the positives are winning by 1, and that's why it forms a +1 charge when it loses that electron. How about magnesium next? Magnesium's number 12. It's so close to being like number 10, argon. It just needs to lose 2. So if it loses 2, then it will be Mg2+, for the same reasons as potassium, only it's got 12 positive protons. It had 12 negative electrons, but it lost 2, so now it only has 10. So +2 charge. How about bromine, number 35? Bromine is so close to being like krypton. It's 1 away. It needs to gain 1. So it had 35 positive protons and 35 negative electrons, but if it gains 1, it has 36 negative electrons. So now the negatives are winning by 1, and it will form the ion Br-. And O, I just saw this is an error. O is number 8. And so the symbol that, or the oxygen atom wants to gain 2 to be like neon. 8 to 10, it needs to gain 2, so it will form a -2 charge. And phosphorus, number 15, is so close to being like argon, number 18. It just needs to gain 3, so it will form P3-. Define the terms cation. It's an ion with a positive charge. And anion, it's an ion with a negative charge. And give an example of each. So let's see. A cation would be like K+, Mg2+, and an anion would be like Br-, O2-, or P3-, anything with that negative charge. List 3 elements that would combine with oxygen in a 1-to-1 ratio and explain why. Oxygen, we just learned in the last question, it wants to gain 2 electrons. Okay, another way of drawing this is to see that it's got these 2 holes here. It wants to gain 2. So a perfect match would be something that wants to lose 2 electrons. So that would be like magnesium, for example. Magnesium wants to lose 2 electrons. So it could be the perfect match. Anything in group 2A, in fact, all of these want to lose 2. Like Be wants to lose 2 to be like helium. Calcium wants to lose 2 to be like argon. So other examples would be Be and Ca. Oxygen wants to gain 2 electrons, and elements in group 2A want to lose 2 electrons, so they form a 1-to-1 ratio. When magnesium and bromine combine, they form MgBr2. Explain why they combine in a 1:2 ratio. Mention what's happening to electrons. It may help to sketch a picture. Okay, magnesium is in group 2A. It's got 2 electrons that it wants to lose. Bromine is in group 7A. So it's got 1, 2, 3, 4, 5, 6, 7 in its outer shell, and it wants to gain 1. So magnesium can lose one of its electrons to a bromine, but it's not satisfied because it wants to lose that other one. So you need 2 bromine atoms in order to satisfy the 1 magnesium. Boom. Oops, didn't draw my arrow very well. Now magnesium will have a positive 2 charge, and each bromine will have a negative 1 charge. So if you add up all of these charges, they add to 0, and that makes it a neutral, happy, ionic compound. Explain why most transition metals need Roman numerals in their compound names. They can form multiple cations. So you know how like magnesium always loses 2 electrons because it's in group 2A. Copper can sometimes, copper is Cu. It can sometimes lose 1 electron to be stable, and sometimes it loses 2 electrons to be stable. So it's complicated. You can take inorganic chemistry in college and learn all about metals. So we've got to keep that in mind as we do some names if there's a transition metal involved, which I just noticed there's not any transition metals in number 33. So we got off easy here. So name these compounds. So we have to look up the names and change the ending to "ide." So NaF is sodium fluoride. K2CO3, we need to check our polyatomic ions. CO3 has a special name, it's carbonate. So this one is potassium carbonate. We don't have to do any work really. The next one, instead of lithium sulfur, it would be lithium sulfide. We change that ending to "ide." And the next one, calcium, we look up the special name for PO4. It's phosphate. And NH4 also has a special name. It's ammonium. And instead of iodine, it would be iodide. Change the ending to "ide." And then we've got aluminum, and let's look up the special name for NO3, nitrate. And now we do the reverse. With writing formulas, though, we want to crisscross the charges. So copper, if we look up its symbol, it's Cu, and the Roman numeral 2 means it has a +2 charge. Chlorine is in group 7A, and you can just look at the charge above it. It's -1 on the periodic table, -1. So this would be CuCl2 for the final compound. Lithium nitrate. Lithium is a +1. Nitrate is one of the special ones on the chart. It's NO3 minus. So NO3 minus. So it would be LiNO3. And then nickel, Roman numeral 3, selenide. Se, if we look it up, is in group 6A, which means it has a -2 charge. So we crisscross the numbers, not the charges, and we get Ni2S3. Again, that's because nickel wants to lose 3, just to draw this out, and selenium wants to gain 2. So in order for these to work out, you need 3 seleniums to satisfy the 2 nickels. And then each nickel has the +3 charge, and each selenium has the -2. And so if you do the math on this, +3 and +3 is +6, -2, -2, -2 is -6, and so those cancel out. And last but not least, manganese is Mn, and if it's got a +4 charge, when it combines with nitrogen, -3, that forms Mn3 and 4. Crisscross the charges. Then we're in our most recent unit. Yay, we're in the home stretch. Explain what honk 1, 2, 3, 4 means. It means hydrogen atoms form 1 bond, oxygen atoms form 2 bonds, nitrogen atoms form 3 bonds, and carbon atoms form 4 bonds. Use the molecules H2O, ammonia, and methane in your explanation. So H2O would look like this because hydrogen atoms form 1 bond and the O would form 2 bonds. Ammonia would be NH3 because nitrogen forms 3 bonds and each hydrogen forms 1. And carbon would want to form 4 bonds with hydrogen because carbon needs 4 bonds and each hydrogen needs 1. Draw 2 isomers for C3H6F2. Well, fluorine is able to make 1 bond. And so are the hydrogens. So one option would be to have both fluorines on 1 carbon, or another option would be to have 1 fluorine on the middle carbon and 1 fluorine on the end carbon. Or another option could be that you put both fluorines on the middle carbon. So this is a great application of what an isomer is, a different arrangement of the same exact formula. And that results in completely different properties with these molecules. What is the octet rule? Atoms want to surround themselves with 8 valence electrons. The great 8. Are there exceptions? Yeah, some small atoms like hydrogen are happy surrounded by just 2 instead of 8, by just 2 valence electrons. So, i.e., hydrogen. Okay, then we're supposed to complete the table by drawing Lewis dot diagrams and writing the number of covalent bonds each will form. So P number 15 is in group 5A. So it gets 5 dots and it's got 3 lonely dots, so it will form 3 covalent bonds. Hydrogen is in group 1A, so it gets 1 dot and it wants to form 1 bond. Fluorine is in group 7A, so it has 7 dots and it wants to form 1 covalent bond. So let's put this to work. N2H2. We want to draw this formula. So molecules like to be symmetrical. Nitrogen gets 5 dots because it's in group 5A. And I'm going to put 2 hydrogens on the sides, and I'm going to connect everything once. There's 2 lonely electrons between the nitrogens still, So that must be a double bond. So I'm going to redraw this neatly with kind of like an equal sign between the nitrogens. How many bonded pairs and lone pairs does your molecule have? So bonded pairs, it's got 1, 2, 3, 4 bonded pairs. And lone pairs, I'll highlight in green, just 2. For the following molecules, draw the Lewis structure and name the shapes. Include all lone pairs. So first one, C3H8O. So let's see. We've got a carbon with 4 things attached, another carbon with 4 things attached, a third carbon with 4 things attached. So 1, 2, 3 tetrahedrals. And around the oxygen, 2 things attached and 2 lone pairs. That's a bent shape. CH5P. Phosphorus wants to form 3 bonds because it's got 3 lonely electrons. Oops, I don't know why I did this for the carbon. Carbon's got 4 lonely electrons. So for the shapes, we've got 1 tetrahedral because the carbon has 4 things attached, and the phosphorus has 3 things attached. So we know it's trigonal something, but it's got 1 lone pair that's pushing the other 3 down. So that would be trigonal pyramidal. H2O2. Oxygen has 6 dots, 2 lonely electrons. So we'll connect them once and fill in our 2 hydrogens. So each of these is a central atom, 2 things attached, 2 lone pairs each. So that's 2 bent shapes. And the last one, we've got CH3S with an F. And this one, I was expecting there to be a trigonal planar one, but there's not. There's a tetrahedral and there's a bent. So lots of good practice with drawing and shapes there. So woohoo, great job. Wow, that took an hour. That was crazy. That's everything from the whole semester though. So good luck. I hope that was helpful.